problem is asking us to consider the total production of a product that depends on labor. That's a variable L, and a capital investment. That's a variable K. And so they talk about a Cobb-Douglas model that is a function of L and K. And so we want to maximize that given a particular constraint. So let's write that out. We're going to maximize our P function, which is a function of L and K, and the P function is a constant B, a positive constant B, L to the alpha, and then K to the 1 minus alpha. We're trying to maximize that with a given constraint. And our given constraint is m times L, and added to n times K is equal to P. So this is our setup, and this looks like it's a Lagrange multiplier type of problem. And so we introduce our multiplier lambda when we find the gradients of P and the gradient of G, where G is a function of L and K as well, and it's equal to ML plus NK. So let's take our gradient here, piece by piece. We got P is the derivative of this function with respect to L. So B and K and alpha are all constants. So let's take the derivative with respect to L. Alpha goes down, and then we got B that didn't do anything, and you have L now with one less power, and then K 1 minus alpha. So that's the derivative of the P function with respect to L. Now for the second component of the gradient, we want the derivative of the P function with respect to K. Again, B and alpha are constants, and in this case L is constant as well. So BL to the alpha, and then the derivative of this is 1 minus alpha times K to the 1 minus alpha minus 1. So that's just negative alpha, but we'll leave it like that for now. Now we take the gradient of our G function. This one's going to be considerably easier. We're going to focus on this, take the derivative of that with respect to L first, and NK is constant, so we just have M, and then derivative of this with respect to K is just N. So this is our pair of gradients. We're going to set equal each other with an alpha, and so we can write that out as our three equations that we're looking for that we will eventually have is alpha times B times L to the alpha minus 1 and K to the 1 minus alpha, and this is going to equal to lambda times the first component of the gradient of G, and that's M. And then let me move the 1 minus alpha out here in front, B, L to the alpha, and then K, and then let's just cancel the ones here. This is a negative alpha power, and this is equal to lambda N. And then so we have the unknowns are L and K and lambda, so we have three unknowns. We're looking for a third equation, and that's going to be the constraint. ML plus NK is equal to P. Now, we're going to try to solve for this system of linear equations, and the first thing that we can notice is that ml times nk is equal to p, and we have m and n here. So what might be an interesting idea would be to think about dividing by lambda, but before we do that, let's think about multiplying this first equation by L, and I'm going to have an ml here, and if I take the second equation and multiply that by k, I'm going to have an nk there. So if I add those two, after I get rid of the lambdas, if I add those two, I should get this thing to equal to p. So let's rewrite our functions. Let's take our first equation and multiply everything by L, or multiply both sides by L. I'm going to get alpha times b, and now I have an L to the alpha minus 1 times another L, so that's just going to be L to the alpha power. And then k to the 1 minus alpha didn't change, and this is equal to lambda ml, and then we will take our lambda and divide that out, bring it to the other side, if we want to think about it that way. And we'll do that right now. So ml, after you divide out by lambda, is going to equal to this stuff. And then after that, we'll do the same thing. This time we'll look at k, multiply k through. So I have 1 minus alpha times b, you got L to the alpha, and now you have k minus 1, and then you multiply that by another k, so you add 1 to that. So this is going to be minus alpha plus 1. Well, that's the same thing as alpha minus 1. And this is lambda, and then this is n, and we multiplied it by k. Again, you divide out by alpha, you get nk is equal to 1 over alpha, or 1 over lambda, times the rest of this stuff. And you see, one neat thing about this is that they all have common terms, and so when we're going to add this is going to be our next step, we will add this, and then we got ml plus nk. That's, let me write that over here, ml plus nk is actually our constraint p. And so we're going to add this side. Let me add it by factoring out the things that we already have in common. And so what do we have in common? Let's circle the ones in common. We got 1 over lambda, and we got everything else except for the alphas. So let's put everything in common and factor out everything in common. So that's b, l, alpha, k to the 1 minus alpha. And then what do we have left after we add? We have alpha plus 1 minus alpha. And then we'll see that that simplifies. You get the alphas canceling out, and that's just 1. So eventually we'll have p equals b l sub alpha k, or l to the alpha power k raised to the 1 minus alpha divided by lambda. So we might be interested in solving for lambda here. We do want to solve for L and K, but I think at this point let's first solve for lambda, and then we'll use that information to solve for L and K. So we got lambda is equal to b L to the alpha k to the 1 minus alpha divided by p. Alright, so now what we'll do is we will take this and put it into each of these first two equations, and then hopefully be able to solve for lambda, or for L and then K. Alright. So let us take the first equation. We have alpha times b L to the alpha minus 1 times k to the 1 minus alpha power is equal to lambda times m. So the lambda, let's see, write this a little bit neater, 1 over p, and then I have the numerator is b times L to the alpha k to the 1 minus alpha, and then times m. So this whole thing is actually equal to lambda, and that's what we were setting that equal to. Now, if we look at this carefully, we are interested in solving for L or K, and then we see something nice happening here. We have the B's will cancel. We have the K with the same power goes away, and then so what do we have left? We have L and L. Now it looks like if I divide by alpha minus 1 both sides, I'm just going to get L. And so I want to bring this to this side, so I'll have L on the right hand side. And now I have to bring the M and the P over to the other side. So if I bring the P over, it'll be in the numerator, and then there's still an alpha left. And then if I divide by M, it'll be in the denominator. So this is my solution for L. Alright, similarly, we can take this lambda and put it into this second equation. So let's start writing that out. We got 1 minus alpha b L to the alpha k to the negative alpha is equal to lambda. Again, I will rewrite lambda as 1 over p L to the alpha k to the 1 minus alpha, and then times n. Again, this is lambda times n. So we see things canceling again. We have, oops, I forgot the b over here. Oops, I mean this b over here. So let's put that back. That came from the lambda. Okay, now we can cancel. Cancel the b's. Cancel the l's. They all have the same power. And now I have a k raised to the 1 minus alpha, and I have k to the negative alpha. So if I divide both sides by k to the negative alpha, they would cancel and leave me with 1k left. So I'll have k on the right hand side, and then I want to bring the n and the 1 over p to the other side. So 1 over p in the denominator goes to p onto the numerator on the other side. And then n goes in the denominator. And that's my k. And so that's exactly what they have here. You got the L and the K, the same L and the same K that we got. And we showed it by using Lagrange multipliers. Alright, so I hope that helps, and good luck.